Okay, good afternoon, everyone. Good to see you on this Friday before Thanksgiving. It's a great pleasure to welcome Dr. Carlos Hidrovo, who's an associate professor in mechanical and industrial engineering at Northeastern University. So I actually don't remember the first time I met you, Carlos, but it's a while ago. So
in the middle of the country, in Texas.
In Texas, that's right.
I'm thinking 2010 or 11, 10 years
Something like that, a little while ago. Carlos earned his PhD in mechanical engineering at MIT, and as you heard, he was in Texas for a while. He's been here at Northeastern actually for a couple, oh gosh, I don't know how many years, but a while. Carlos is the recipient of a NSF Career Award in Fluid Dynamics, a DARPA Young Faculty Award from the MTO, Microsystems Technology Office, and an ASME Robert T. Knapp Award. He's going to tell us today, he offered several really interesting talks, but today he's going to talk about gas-liquid droplet microfluidics. So I'm going to pass over to you, Carlos. Before I do that, just to remind the audience that you can type your questions into the Q&A box, if you wish, as we go along. At the end of the seminar, when we have some questions and discussion, if you'd like to ask those questions in person, we can elevate you to be able to do that, or we can ask them for you from the Q&A window. But keep the questions coming, please. So with that, welcome, Carlos, and over to you.
Thank you, Beverly. So yes, so I'm going to talk to you today about gas liquid droplet microfluidics, and we'll start with some fundamentals and then move to some of the applications that I also work in this area. So what you're seeing here on the title slide, it's basically a microchannel that is made on PDMS, the polymer, as you guys know. The dimensions, to give you an idea, it's about 100 microns is the width of the microchannel. And you can see these liquid droplets that are coming out of a liquid inlet. And then on this side, I hope that everybody can see my pointer, on this side channels, you are having air flowing. So you have these liquid droplets being formed in this gas flow. And this is not in real time. This has to be slowed down because these processes can be quite fast. But you can see a number of droplets being formed, and that's what I'm mainly going to talk to you about. It's this formation of liquid droplets in these channels and how we can use those for different applications. So to put things in perspective, let's talk a little bit about the general field of microfluidics. So microfluidics, 20 years ago was a brand new field, mostly at the research level, university levels, field where most of the things that were being done back then were, fundamental research, trying to understand, well, we have these little channels and we can create things in these channels. What useful would there be? Most technologies that come from the universities, at that point, we didn't know exactly, but nowadays microfluidics have become a real thing. So if we look at the market, the global microfluidics market research, it's a $12 billion industry that's expected to be in 2025. And most of these technologies have been used in biomedical and healthcare applications. I'll show you just another example of where the field has gone. There's the two startup companies, one from California and one from here in Massachusetts. These were microfluidic technologies, and I'll talk about the particular one related to Quanta Life. This is a Droplet digital PCR technology, and Rain Dance also sort of does something similar. But both of these companies were bought by Bio-Rad. I'm very aware of how much the Quanta Life acquisition was about 162 million. Not sure about Rain Dance, but these startup companies in microfluidics were bought by Bio-Rad, which is a major biotechnology and healthcare company, and this gives you an idea of where microfluidics is. So it's at this point, it's a mature field with hundreds of companies. If you do a count, about 280 companies worldwide that are in this space, and they're worth upwards of 100 million and with $1 billion market value. So it's definitely a mature technology. It didn't start that way. And what I'm going to focus on mostly, or what I'm going to focus in here, it's the field of droplet microfluidics. And most of the work that has been done in droplet microfluidics and the research has been in the liquid-liquid space. I'm showing here some of the initial work that was done in Howard Stone's lab back in the early 2000s when he was at Harvard, related to understanding the formation of droplets. As you can see here on the left, you have, instead of having gas, as I'm going to focus on, you have oil-based continuous flow leading to the formation of the liquid droplets. And these are considered focusing geometries. On the right-hand side here, what you see is what's considered a T-junction geometry, which we're going to look in more details. But essentially, the work that was started, in the early 2000s in microfluidics was on liquid-liquid droplets, and that's what has evolved now into the more commercial applications. In terms of the dynamics, this is also from sort of from the same group, from Howard Stone's group. Most of the work that has been done in understanding the formation of these liquid droplets in these oil flows relates to two major sorts of dynamics. So one is that the flow control dynamics are arising due to hydrodynamic pressures. So essentially the pressures that come across because you have a viscous flow in a confined space. So the oil flowing through these spaces leads to pressure gradients that then lead to the formation of the liquid droplets. And there's also a bit of kinematics prescribed efforts where if you think about, in this case, you would have the oil flow coming this way, the liquid flow coming this way. The oil flow is going to start pinching the liquid, the water flow, and end up with the droplet formation. So that's in essence the basics that we understand in this liquid-liquid systems. There is hydrodynamic pressure, which we'll see again, and also kinematics that lead to the droplet formations. And this is typical of the system because they work at very low Reynolds number, where basically inertia is not substantial. Now, when we think about liquid droplets in a gas medium, well, that's not new. There is a lot of work that has been done in terms of liquid droplets in a gas medium, not in another liquid medium. So if you think about a fuel injector, that's basically liquid droplets in a gas medium. The same thing with an inkjet printer. You're creating little droplets of a liquid in a gas medium to basically create your printing manuscript. So this is not necessarily a new idea, but in all the systems or in this applications, you have liquid droplets being formed in a highly external flow on a quiescent flow of air. And the dynamics of this, go back to the study that Raleigh and Plateau did about, instabilities in jets forming droplets. This is in the 1800s. So this is not a new field. Now, the understanding of these liquid droplets in gas flows for smaller dimensions has taken a little bit of more time, right? It's taken about 100 years if you want to think about Raleigh Plateau's work on the jetting instabilities. Things have had to wait a little bit to try to deal with more smaller dimensions. And most of the work that has been done on gas liquid droplet microflows at small scales coming from a group in Seville, in Spain, from Ganan Calvo. And what he's looked at, it's the formation again of what you have here is this, and also you have a liquid flow that then he tries to squeeze through this little hole or aperture. So you have air surrounding this jet, and you're trying to push the liquid to a small aperture through the jet through a gas flow on the side. So like a co-flow besides the liquid jet to basically create then a filament that breaks up into droplets. So the idea here is that you get this jet formation through the inertia of the liquid water or the liquid that you're creating the droplets in. I think it's also water. I think he used hexadecane, if I'm not mistaken, but some oils. But basically, you get the formation of the jet by the inertia of the liquid flowing out of the nozzle. And the other thing that he was able to ascertain when he looked at the droplet size or the jet size and droplet size formation as a function of the flow rate of both the liquid and the gas was that the jet dynamics were governed by Bernoulli's behavior. So like an inertia-based behavior. So in essence, what he was saying is in the liquid flow, you can apply Bernoulli's equation, which is a trade-off between pressures and kinetics. And the pressure, it's basically imposed by the gaseous flow outside. So those are important things to understand because he basically considered the liquid flow as mostly not viscous, and the gas flow also non-viscous, but the gas flow, which would have had some pressure drop due to viscous effect, will impose the pressure on the liquid, and that's what leads to the jetting formation. Now, I'm going to take you a little bit onto how I got started and how most people, or perhaps me, got started in this field, and that had to do with water management in fuel cells. So the reason I got interested in these liquid droplets in gas flows, and a lot of people did several years ago, was because in fuel cells, what you have is the formation, or you have an electrochemical reaction where you take hydrogen and oxygen, and you combine the hydrogen and oxygen, and that combination produces electricity. So it's the opposite of electrolysis, where you take an electric current to split the water. In here, you take hydrogen and oxygen, you mix them together, that provides electrochemical reaction that gives you a production of current, but in the process, you also create water, opposite, like I said, of electrolysis. So that's the main thing with the fuel cells. Now, this production of water happens on the cathode side. And in order to make these cells function efficiently, usually the channels where you put in the hydrogen and the oxygen are very small. So one of the big issues with fuel cells is that this water formation on the cathode side usually leads to these liquid droplets being formed on a gas flow. And you have to make sure that you're able to remove the liquid droplets from the gas flow channel. So here you have a liquid droplet, and you have your gas flow channel. If you're not able to remove these droplets, you're gonna get flooding. You're gonna get too much water accumulated in the microchannels that you're using to bring in the oxygen into the reaction, and you're gonna stop the reaction. So there was a lot of work being done on trying to understand the formation of these liquid droplets in the cathode channels of fuel cells, and more importantly, what were the mechanisms that allow for the removal of these water droplets. So I'm here showing a couple of works from group in Rochester Institute of Technology, that look into that sort of behavior, try to understand how the droplets were formed and so forth. That was exactly the same thing that I was doing back in those days. I was at Stanford at that point as a postdoc. And what we were trying to do was sort of simulate this behavior. But what we did is we created a proxy. So what you have here, it's a view of, this is a silicon chip where you etch microchannels to try to replicate this process. And then what you have here is a microchannel where you can have airflow. So that's the U-shaped microchannel. And then we created another microchannel on the silicon that was perpendicular to it to create water injection. So we will simulate the behavior of water coming in from the fuel cells, creating these little droplets at the surface of what's called the gas diffusion layer, which is where the Doppler forms, and then sort of being removed. And what I'll show you, it's a video of what you have in the bottom is experiments showing the water coming in, the droplets being formed, and then being carried away by the airflow. You can see the airflows are substantially high, so 20-something meters per second. This one 13.33. As you increase the airflow rate, the water size of the droplets goes down, and we'll talk a little bit more about that. The thing that you're seeing on top is two simulations, and obviously the simulation in the middle replicates the behavior of the experiment very well. The one on the top doesn't. The main thing with the middle simulation is we're taking into account what we know as contact angle hysteresis. If you don't take that hysteresis into account, what happens is you get much smaller droplets being ejected from the air, so you don't seem to have flooding. But if you take into account the formation or the fact that you have this hysteresis, which is the fact that droplets sort of want to stick around because the contact angle has a certain amount of leeway, you get much smaller droplets. The other thing that you can get from this video is that the droplets tend to ride on the wall for the most part. So, I started looking at this, like I said, when I was at Stanford, but then also as Beverly mentioned, I was at Texas before coming to research. So I was starting to look at this process and continue to do that. And, I did a lot of studying on trying to understand, okay, what are the dynamics that lead to this droplet removal from these microchannels? What are the forces that I'm looking at that would allow me to remove these droplets? So if I define my droplets in terms of the length, and I actually wouldn't even call them droplets, better to think about them as slugs of liquid. And if I think this slug has a length of L and a height of H, and I can define my microchannel height, I can go ahead and do a series of experiments where I vary my gas flow rate and then look at what the droplet shape is. And that's what you see here. You see here different slugs sizes as you increase the Reynolds number of the gas flow on the main channel. And not surprisingly, what happens is as you increase the gas flow rate, the Reynolds number goes up, you start getting high inertial effects, the droplet size goes down. So the question is, what kind of forces do we have in this geometry, T-junction? So I'll give you a little non-dimensional analysis on the things that we look at to try to understand what are the major forces. So again, you have the slug here. This is a cartoon of what you guys saw before. You have the length of the slug, the height of the slug. This is the height of the channel. You have a width of the channel into the page. And you can see here that hysteresis of the contact angle. The contact angle at the front is larger than the contact angle at the back. And we can talk about the mean velocity of the air based on my gas flow rates and so forth. So based on this, we come across to try to define certain types of dimensional numbers that we're familiar with that would give me an idea of what the relevant forces are. So the capillary number, as we know, gives me the ratio of viscous forces to surface tension. So I call this the modified capillary number because if you look at the capillary number, usually that's just viscosity, characteristic velocity over surface tension, and there is no length scales involved. But to kind of be more specific about the situation we are looking at here, what we really decided to do was look at what would be the shear stress force due to the air coming in this small space here, right? The air has to squeeze to the top of the slug. So what would be the shear stress on the top of the surface compared to the surface tension force? And that's what you see here. This is your typical capillary number, but it's being modified to account for some of the geometric constraints that you encounter in this system. We also look at the Weber number. The Weber number, it's the inertial force over surface tension. And inertial force in this case comes from the fact that I have this air coming through. The viscous shear stresses happen because I get a squeezing. But the droplet also represents an obstruction to the airflow. So the airflow coming through here, a lot of it has to basically stagnate, right? This is the equivalent of me sticking my hand out when I'm in a car. You feel a pressure in your hand because the air has to come to a stop. And that's what this Weber number is giving me. What's happening in terms of air that needs to stagnate because there is an obstruction. And again, we did some modifications to account for the geometry and came out with this modified Weber number where now I'm looking at a possibility that not all the air is just squeezing through, but some of it might be stagnating on the forward part of the droplet. And then the last one, and I didn't have a name, there is not a name for it, so I decided to name this the drag number. One of my mates at Stanford later pointed out maybe calling it hydrodynamic buoyancy. But this number has to do, and it's similar to the analysis that was done in liquid-liquid system, has to do with the fact that you have a confined air moving in the channel. So we know that because of viscous effect of the air, you're going to create a pressure gradient on the channel. Well, that pressure gradient is going to impose a force on this log. If I look at this number, it's going to look very similar to the capillary number because it has, and you can see that, it has the viscosity of the air and so forth. But what you see here is got the friction factor and the Reynolds number, my Posable number, my FRE number. Because even though it's a viscous-based force, it's not the shear stress on the top surface of the droplet. It has to do with the pressure difference that the droplet is experiencing. That pressure difference is coming from the confinement effects of the air. So those are important things to consider because when we now look at the values of these numbers, and I'll give you attention. So I'm going to plot here the capillary number. It's very small. So the shear stress is really not substantial in terms of what's driving these droplets. But if I look at the Weber, which is my inertial force, and this drag number, which has to do with my hydrodynamic buoyancy, my pressure gradient sort of trying to move these droplets, what I see is, what I have here is this blue squares and magenta triangles. This is my drag number, so my hydrodynamic pressure. That starts somewhat high, but it substantially goes down as I increase my Reynolds number. As I increase my Reynolds number of the air, the effect of this hydrodynamic buoyancy, if you will, starts to decrease. Conversely, my inertial effects, my Weber number, which is the hand effect where the air has to stop, they start to become higher and dominate. And you can see this crossover at about a Reynolds number of the air of 200, where it appears that the dominant force is that of the inertia of the air rather than the pressure drop. I did this stuff also in my lab when I was in Texas, and we got very similar results. These are not as easy to see, but essentially what you have here is the viscous force, the pressure force, and the inertial force. The viscous force you can't even see because, like I said, it's very small. The pressure force and the inertial force are the ones that you can see here, sort of having this, again, crossover behavior that you also see here. All right, so that's in terms of this T-junction geometry. One of the things that should have been apparent is on this T-junction geometries, you get a lot of the droplets riding on the walls of the channel. So there's a substantial surface tension effect as I try to remove the droplets. So, you know, as I move through my understanding of this system, the question was, well, can I actually, instead of just thinking about, you know, how liquid droplets get removed on fuel cells, can we control the formation of liquid droplets? So can we do what people do in liquid droplet microfluidics and try to see if I can control create controlled liquid droplets on the gas flow based on the understandings that we have. And there is some other people that have worked in this area. I'm showing at the left this is sort of a supersonic nozzle from the Whiteside's group, where they've been looking at trying to create liquid droplets in gas flows. They create rather than specific small droplets, they create more of like a big spray of them. But the idea is to try to create these liquid droplets in a confined gas flow. And another group in the University of Maryland, from John DeBow, has looked at the use of capillaries to try to create these liquid droplets, but now in a co-flowing geometry, right? Rather than having your T-junction, now you have flow flowing through the sides. And he was able to create somewhat monodispersed droplets. There's, you can see the size here, 500 microns to about 250 microns. So he was able to create some of these droplets, and to a certain extent, you could say that in a controlled fashion, right? The ones in the right-hand picture here are not all that uniform, but the ones on the left are. So there is some control of the droplet formation. I also started working on this area around maybe the same time, a little bit before, about trying to control the droplet formation. But instead of using off-the-shelf capillaries, I decided to try to create these microchannels on PDMS, also using the same techniques that you used before. So here you have the PDMS channel. This is basically what you guys saw in the initial slide, which is we have airflow through these side channels, liquid flow through the middle, and we can create, as you can see here, these droplets. So some of the things that we have done, what you have here is the airflow rate on the vertical axis of the gas flow, the water flow rate, and depending on the combinations of gas and liquid flow rates, you can get droplets, you can get what I'm gonna call more jetting, we'll talk about this more, and even just stratified flow, where you don't really get droplets, you just get stream of liquid flowing besides the gas liquid. But basically this gives you a little bit of a regime map of how this system behave. We have improved some of the behavior of the system by doing treatment of the walls that are non-uniform. So one of the things to make sure that droplets are formed is to try to make the surface, for the most part, hydrophobic. PDMS is hard to make hydrophobic, but if you heat it up, it becomes somewhat hydrophobic. What we found out is that if we make one of the surface, the PDMS wall, the top wall in this case, slightly hydrophobic, and the bottom wall, instead of using PDMS, we use a glass slide and create a slightly hydrophobic glass bottom, we were able to do better control of the droplets. So I'll show you here a video where we're doing a more involved regime mapping of these droplets, and rather than plotting the gas flow rate and the liquid flow rate, we make the mapping in terms of the Weber number of the liquid and the Weber number of the gas. You can see here what we call the plug-in regime, where you create sort of big droplets. This is the dripping regime that we're going to spend a lot of time talking about, or spend some of the time talking about, which is where we're going to focus. If you keep increasing the airflow rate and the liquid flow rate, you can get to the regime you saw before, which is sort of satellite droplets, and then the jetting regime, which we'll deal with at the end. All right, so we focus now on the dripping regime. After doing this analysis of what conditions lead to what different flow regimes, the dripping regime is what we want to work on, because this regime allows us to get uniform droplets that are very controllable. So we're going to do an analysis of what the forces involved are, so like we did before, and we're going to have surface tension of the liquid coming out of the liquid injection site, the gas inertial force. So that gas coming from the sides, it's going to encounter, as the liquid droplet grows, an obstruction, and it's going to create a force. And if we do that, we can come up with a formulation for what, by balancing these two forces, what should the width of the droplets be in relationship to the gas flow rate. That's what you get if you do a balance of the surface tension with the gas inertial force. Similarly, we wanted to look at the frequency. So what you're seeing here on the left, it's the frequency of droplet formation. It's been non-dimensionalized by these two quantities. I'll get into that. And what we see, there is a linear relationship between the frequency of the droplet formations and the product of the gas flow rate and the liquid flow rate, okay? Both these gas and liquid flow rates have been non-dimensionalized, so these plots are obviously non-dimensionalized. But what you see is a linear relationship of the frequency of droplet formation with the product of the gas and liquid flow rate. And to understand that, well, it's easy to see that the liquid flow rate and the droplet volume will be related by the frequency. So the frequency of droplet, the droplet formation times the volume of a droplet would give me the liquid flow rate. So that's sort of easy to see what that relationship is. With the gas flow rate, maybe it's not that easy to see, but if you think that the liquid or the volume of the droplet is proportional to the width of the droplet, the length of the droplet, right? Because they're not always spherical. And then the height of the channel. So this is equivalent to the droplet volume. We can see that the length of the droplet, which is related to the volume of the droplet, and then obviously inversely proportional to the frequency, the length of the droplet is going to be related to the gas flow rate in the same way that the width of the droplet will be. So both the width and the length of the droplet are going to be inversely proportional to the gas flow rate. The higher the gas flow rate, the smaller the droplet. And that's what gives you then a frequency that is proportional to the gas flow rate times the product of the liquid flow rate. If we non-dimensionalize my droplet width and my droplet length with the minimum width that we can measure and the minimum length that the droplets can have, and these are related to the geometry of that nozzle sections that you saw, we see this behavior, which with the Weber number of the gas, which is essentially the gas flow rate, which says that, yes, the width and the length of the droplet both decrease with increasing gas flow rate and Weber number of the gas, but they eventually plateau at a certain point, and that has to do with the fact that you have a finite liquid channel over which the droplets are formed. So if you think about when you go from the droplet formation to just the co-flowing jet, that's the sort of limiting factor where you won't get droplets being smaller than the liquid channel size, okay? However, that's not the whole story. Inertia is not the whole story. We also have a little bit of issues related to the hydrodynamic pressure. And what I showed you before are conditions where inertia is mostly dominant. But if you throttle back a little bit the gas flow rates, you can have the same things that you saw for the T-junction situation, where you had this hydrodynamic buoyancy taking effect. So what I'm showing here is another analysis that we have done in my group, trying to address using simple control volume of the injection section. What is the balance between these forces based on the flow rates? And what you see is that we get this effective diameter. What we would say is the volume. Effective diameter would be the droplets are not spherical, right? You have these elongated slugs. So the effective diameter would be, if we take our elongated slug and make it into a spherical droplet, what would be the diameter of it? And what I'm showing here is the experimental data, and you see two bounds. And the reason we have two bounds, it's because you kind of need to know the pressure in this section, the pressure of the flow in this section, and that's something that we can measure directly. We can measure the overall pressure drop of the gas. Because it's a two-phase flow, there is fluctuations of the pressures, and this fluctuation leads to an uncertainty on what exactly will be the pressure that you're experiencing, the pressure drop in this section. So the reason you're seeing this upper and upper bounds are based on this uncertainty of what the actual pressure difference would be in this region. But we're able to kind of get somewhat of a good matching of the behavior of our data with our model. And what this tells us is that, again, there's going to be conditions where you're going to have a balance, or not a balance, but you're going to have, in addition to the inertial forces, sort of these more viscous-based hydrodynamic buoyancy forces. So we do have inertial effects, but that's not all the story. And in certain cases, you're going to have to take into account these viscous effects. All right. So that sort of gives you an idea, sort of the fundamentals of this droplet formation, where hopefully I have provided you with an understanding that as we go to this gas-liquid droplet microfluidics, you have to take into account the inertial forces. The viscous forces that you have in liquid-liquid systems are still there, but as you try to move things forward and you know, create or increase frequency of droplets, create smaller droplets, because higher gas flow rate leads to smaller droplets, you start to deal with smaller droplet size, and that means more inertial forces. So I want to move now a little bit to applications, and I'm going to start with micromixing. So microfluidics obviously give you a lot of benefits because you can have very small reactions sizes. You know, you can make very small droplets. You can also create a bunch of them, so you can do multiplexing. You can, instead of having, you know, one experiment, you can create millions of experiments. If you create each droplet gives you a different experiment. So that's the benefits. But the fact that you have usually low Reynolds number means that you're in laminar flow, which means that most of your mixing is controlled by diffusion. You don't have the advection effects that you have in turbulence, because most of the flow is laminar. So just to give you an idea, if you look at the characteristic diffusion time, which is going to be your characteristic length scale over the diffusion constant coefficient, if I were to try to mix two teardrops, right? If I think about a tear, size of a tear, very small, that's at 6.5 microliters. If I try to mix two tears, let's say that I put a dye in one of my tears and the other one it's a standard tear, it will take about 22 minutes for these things to fully mix just on diffusion base. So in order to increase mixing, what you would have to do is take your tear and divide it in 10 to the 10 times smaller droplets to get to the order of 1 millisecond mixing. So think about that. You know, a tear is already a very small volume, and we would have to create, you know, over 10 giga droplets or 10 giga divisions to get to droplets that are small enough in the order of picoliters or nanoliters, at least, to try to create 1 millisecond mixing time. So this is a problem in microfluidics, the fact that we're laminar. So there's been two methods where we try to increase the mixing, and one is chaotic advection, which we'll talk about. It's not quite turbulence, obviously, but it's the idea of trying to create vortices or vortical structures to sort of mix the dough and create faster, reduce the diffusion length scale, or actually reduce that. So that's sort of what you know, most microfluidic mixers have been based on. One is the chaotic advection. So that's called the baker's analogy. There's a lot of work done in this was in Whiteside's lab in Harvard early in 2000, where they used herringbones to take the laminar flow and basically have it sort of twist on itself. And the twisting motion, as you can see, the baker's dough analogy, created this sort of not chaotic, sort of very controlled advection process that would lead to smaller mixing length scales. So you could improve mixing that way. Mixing times of the systems were still not, you know, great. You were not 22 minutes, but you were in the minute size to 2 milliseconds. And the other possibility was also to use droplets. Now the droplets would be the mixing medium by creating droplets with the two mixing components being flown on a sort of T-junction, and then breaking them apart in a liquid section. You could have now the droplets become this sort of recirculating sections where you would also create the mixing. But like I said, the mixing is still, you know, in the order of milliseconds. If you do hydrodynamic focusing, where you basically take a fluid and you sort of squeeze it with another fluid, you can reduce the length scale for diffusion, as I showed before, and reducing that length scale leads to faster mixing times in the order of microseconds. But that's not enough. So if I look at my diffusion and my mixing time scales, I'm going to have my molecular diffusion, I'm going to have my viscous diffusion length scale. They're very similar. But I can also talk about a bulk convection or mixing time scale, which is just the length, the time scale related to sort of a steering motion, where it would be my length scale divided my average velocity. And this can lead to substantial increases or decreases in mixing time. So here's an idea, or the idea of using sort of these gas liquid droplet microfluidic systems to improve mixing. So you can create one of the droplets on one T-junction, for example, another one in another T-junction, collide them together, and if you collide them together, you basically enhance mixing. And I can do arguments about kinetics of how fast it would take for this droplet to completely traverse this droplet. That's sort of my advection length scale. Or I can do viscous dissipation time scale arguments. And what I get is that if I look at the droplets that I was forming and try to figure out, so a 50 micrometer size droplet, and I can get them moving at 1 meters per second, when they collide, you and I got a mixing time scale that is much smaller than milliseconds and in the order of microseconds in a much larger volume if I consider a comparison with the flow focusing geometry. And that's what you're going to see here. We have here a T-junction that flows into an airflow and creates a droplet. We're going to have the same thing on the other side, creates another droplet, and they're going to collide here at the vertex. The two droplets are going to come together and collide at the vertex. We don't have control of them, so this is sort of happening fortuitous in a way. The fact that we're using T-junction geometry is good because that allows us to slow down the droplets at the vertex, but that's what you're going to see. And you can see here the droplet that was sitting at the vertex come up with another droplet that doesn't have a fluorescent dye, and you can see the mixing that happens as the droplets collide. I'm going to play the video again with pseudocolor. So the droplet here has a fluorescent dye. The droplet in here has no fluorescent dye. As they come together, you're going to be able to see the collision. So the sitting droplet with fluorescent dye, the pseudocolor, and here comes the other droplet that you can see, and you can see the vertical dynamics that lead to the mixing. So we can do a couple of statistics, and I won't go into the details of this, but there's basically two statistics that we want to look at. One is how homogeneous is my intensity, which tells me, mixing is sort of complete. So that's my spatial intensity standard deviation. I want to see, when all my pixels in the droplet have the same color, I have reached full mixing. But the other thing that I can look at is how many gradients I have in space. And that gives me an idea of that advective process, that folding process, right? One way to think about that is if I have, here I have a checkerboard, right? So I have here a checkerboard that only has a black and a white region. All the checkerboards to the right of this checkerboard has the same number of white and black pixels, right? So there is no real mixing. They're all black and white, have the same number. But by sort of steering the system by dividing it into little portions, I have created now a small smaller checkerboard. And most people would say, well, this is not really mixed. I have the same number of blacks and white, but now this checkerboard is stirred. I have a better steering process. That's sort of the effect of the chaotic advection. I am steering and putting things closer together. So that's what we're looking at when I look to the right. As I look downwards, what we're doing is using, a simulation is try to pretend that I have diffusion of the black areas into the white areas. So you can see if I just look at the black and white on the left-hand side, that this is becoming blurred because I'm letting my system sort of diffuse by doing an average technique. But this gives you an idea of what's happening really in the droplets and what things I can be looking at. I can be looking at my average intensity, which if I look here, each one of these graphs corresponds to each one of these checkerboards. They all start the same because the black and whites are all the same in all cases. Even though this is better stirred, there's no diffusion. What you see is that as I move to the right, and I'll explain what that means, I basically start moving to the right, now basically moving down. The system that has more stirring becomes quite mixed faster than the system that has no stirring. So at the beginning, they're both about the same in terms of spatial intensity. As I move downwards, the system that was well stirred becomes mixed much faster. And that's what we're kind of looking at here now is the number of gradients, the number of divisions that I have in my figures. Here I have only one division. Here I have 4, and I can keep on increasing that. So that's sort of what we are showing here. How many divisions do I have? And this is my 2-point division. That doesn't change much. If I keep looking downwards, it's clear that I only have one interface. I only have one interface. The systems where I have substantial stirring, the number of interfaces, so this is my big checkerboard, my number of average interfaces per unit time starts to go down. And they start to go down because I'm getting better mixing. When I get here, I don't have any interfaces present. The one interface that I had here stays constant. I would have here how many? I don't even talk 64 checkerboards, so I have 128, something like that, interfaces that I can still measure here, but as I keep diffusing, I lose all of them. So this is a measure, or this approach allows me to measure both diffusion mixing and stirring. And that's what we can get from those pictures that I show you of the droplets colliding. I have here for different Reynolds numbers of the droplets collision, what my standard deviation of average intensity looks like. So this is basically my mixing times, or my mixing measure, my diffusional mixing measure. And clearly at higher Reynolds number, I get mixing much faster. You can see it's about a millisecond. In the intermediate Reynolds number, the mixing process takes a little bit longer before I get to 0 when everything is at the same level. And then at the Reynolds number of 7, it takes a little bit longer. Something to pay attention to here is this sort of fluctuations in the mixing time scale of the diffusions. And what's happening here? Well, if I look at the number of divisions that I have in the droplets, right? The number of checkerboards that I have in the droplets, what you see is that the droplets that were collided at very low Reynolds numbers, they don't have a lot of divisions because that's equivalent to my 2-piece checkerboard, which only have one interface. The droplet that has the highest Reynolds number during collision, what you see is a substantial number of fluctuations on the number of interfaces, because I'm going to have a lot of those interfaces and I'm going to be creating a lot of them more. And I have this sort of behavior because as I keep stirring, I keep creating more of them. So we have looked at different geometries for these colliders. And what I would point out is that, this 90-degree one is not ideal because even though you're moving at high velocities, because of the colliding angle is not straight on, you kind of lose some of that inertia. But if we create a head-on collision angle, you're able to decrease the mixing times substantially below 1 millisecond. And we were able to get on the order of millisecond with about 50 microliter dropper, which it's something that hasn't sort of been done before. The number also increased substantially as we get into this sort of geometry. So just to finish the Micromixer part and then move to the next application, what I would tell you is that the main thing here is if I look at my mixing time scale, and what I'm going to do is look at the mixing time. I can measure that from the stuff that I showed you before. If I look at the mixing time and I non-dimensionalize it by my viscous dissipation time scale, my diffusion dissipation time scale, and then my convective time scale, what I see is that the blue and the green, which are the mixing time scale divided by my viscous dissipation, by my diffusion length scale, also go down. That's not surprising. As I increase my Reynolds number of the droplet collision, my mixing time scale goes down. So that means I'm getting faster mixing. But if I non-dimensionalize my mixing time by the convective time scale, that's sort of my advective time scale, what I see is that I get a plateau. And what the plateau is telling me is that when I go above Reynolds number of 1 for the collision, it becomes apparent that the dominant mechanism, it's the mixing. It's the fact that once you get to a high inertial collision, the mixing is completely dominated by the steering process. You get diffusion, you're always going to have that, but the diffusion, the length scale of diffusions are controlled by the advection time scale. All right. The sort of the last part that I want to talk about is that of using these droplets for another technique, and I'm going to talk about digital droplet PCR to give you a background on what these droplets can be used for. Digital droplet PCR is basically a technique based on PCR, which is polymerase chain reaction. Polymerase chain reaction is a technology that is used to try to detect a given DNA by doing this denaturation process where the DNA strands are replicated by doing a process of heating up the samples and and then cooling it down, and you replicate the DNA multiple times, and you put a couple of fluorescent tags into the replication process, and what that allows you to do is figure out if you have the DNA that you are looking for and whether that has been present there. So this is a quantitative process where essentially, what you have here is the fluorescent signal from the sample started with one DNA strand. And as you do these cycles of denaturation, the signal goes up if you have your target of interest, because instead of getting just one DNA strand, you're going to end up with 4, and you can see this increasing. So the signal keeps increasing with the number of cycles. That's an analog process. But there is technologies that now allow you to do the same thing, but from a digital perspective. So by using liquid or droplet microfluidics, what you can do is you can create measure the overall signal analogy. You can just say, how many droplets do I have where I can show that I have my target DNA out of the number of droplets that my system has? So now you have a digital system, and we know that digital is better than analog, not really, but it does give you a digital way of counting or doing the PCR, and that's what digital droplet PCR does. So we have taken the same approach on our droplets to try to do measurements of gaseous or airborne targets using our droplets. So instead of looking at, a sample divided into droplets, we're looking at, I got a gas sample, it's going to form my droplets, I interact with my droplets, and that's going to lead to an absorption. And the absorption not only allows me to target or to measure if the target is there, but it's also a concentration because of the digital signal. And the beauty of the digital signal, says my internet is unstable. So the beautiful digital signal, the same way that I talked about digital droplet PCR, is that in addition to looking at the intensity of the droplets, which I can do, and I can look at the average behavior, I can look at the distribution of the droplets, and I can also look at what is the standard deviation of droplet intensity. So I'm going to have a double measurement of droplet concentration. So I'm going to show you a platform that we created to do that. It's going to have our gas liquid droplet microfluidic system. This is gas liquids. Then we're going to collect the droplets in an oil phase, because that's what we need to process them. We're going to create them and sample things in the gas phase, then collect them, and then we're going to process them. It's a fancy platform. I'll show you a video which is better to just give you an idea of what the platform looks like and the operation procedure. So you have here in the video, this is the whole platform. we use a surfactant. That's why you see a little bit of these bubbles being created on the oil bath where the droplets are deposited. You have the droplet creation in the gas microchannel. Those droplets are then collected in this oil reservoir. And then we have a processing unit at the end that allows us to basically look at the droplets in a more controlled manner without having to worry about, trying to analyze them in the gas flow. So I'm going to skip over this. I'm just showing here that we did some analysis of the performance of the platform. But what I really want to show you, it's how we use this platform. So we use this platform to try to sense gaseous ammonia. So we use something called a Nessler reaction. This is the Nessler reaction. When you deposit ammonia on Nessler reaction, you get this dark precipitate. So ammonia reacting with this precipitate allows you to figure out, oh yeah, I have ammonia. And we were able to do the same thing with our droplets. We will create our droplets in their platform that I just showed you. And you can see these droplets being slightly dark here because they're being reacting with ammonia, gaseous ammonia presence in the gas flow that we created. So this is the picture that I'm trying to show you. So some of the droplets are going to show very dark color. They have the ammonia. Some of them are going to be not as dark because they didn't absorb as much ammonia. But we can do the same thing that people are doing for digital droplet PCR, but for a gas target. We can look here. I have 3 different droplets collected. The droplets were collected under different gases that have different ammonia concentrations. 1,000 part per million, 2,000 and 4,000. This is the least ammonia, the most ammonia. And you can see how I have more darker droplets. If I do a count of my population numbers versus intensity, obviously less intensity means more ammonia, I can clearly see that these droplets in here have more ammonia. So I'm gonna have, my average intensity is gonna be lower for the more ammonia that I have. But you can also see that the spread of my distribution changes. So now I have a 2-pronged measurement to try to determine how much ammonia I have. I not only have my analog measure of the ammonia of the intensity, but what is the distribution of droplets? And I can take this, and if I wanted to make the system even cheaper, I can just set a threshold for what intensity I'm going to consider having ammonia and what not, and use that as a way of measuring what the concentration of ammonia is. So in this case, all I'm doing is counting the number of droplets in my population that have ammonia and using that to determine what the concentration is. So here you see that the percentage of droplets that have ammonia or dark droplets increases with my gas concentration. All right, I know I'm coming to the end of it. Yeah. Go ahead, Beverly.
I'm sorry, I was just going to say we're right on 4. So in the hopes of having some questions, hopefully you can.
Absolutely. So I just give you a future outlook. Where are we going with this? This is before COVID. We were thinking about doing a digital droplet breathalyzer. So COVID-19 is obviously one of those things. You could use this system to try to absorb, absorb the droplets and see the target them. Ammonia itself, we had the recent explosion in Lebanon, so there is definitely applications for this airborne target detection. The other one has to do with probing reaction kinetics. So essentially, one of the examples is that of protein folding. Understanding protein folding is key to understanding diseases. And there's already groups that have started looking at, using droplet collisions to increase mixing times and probe these kinetics. What I would say is that they're still limited on the behavior or on the reaction kinetics they can assume the time scale. We have thought about modifying our platform to try to control the collision in a more controlled manner. So that's one. In terms of the fundamentals, something I didn't talk about was compressible effects. The gas flows in these channels because of final flow leads to a lot of compressible effects. And that is something that would have to be understood. And the last thing that I would say is the jetting regime. I talked a lot about the dripping regime, but the jetting regime is where we need to go. And we have created sort of platforms that allows us to do the jetting regime. These are sort of more three-dimensional platforms that will give you a better creation of this jet and then formation of droplets. We have done some analysis on that, but what I want to leave you with, it's a little video that shows you sort of where we are right now in terms of that jetting behavior. Try to talk a little bit about the music, but you see that this is at a rate of 13500 frames per second. We're not even millisecond time scale. So, you know, this is 1/130, 105 per second. This is being slowed down substantially. This is one of the students. This is a great video, but
hard to hear you, Carlos.
Where we are, we can create 20 microfluidic droplets at about 120 kilohertz generation rate. So that's where I see this technology going. You can create a lot of droplets at a very short time, and you can create them much smaller. That was 25. I was talking about 50 microfluidic droplets. So just to summarize, you know, it's an emerging field, gas liquid droplet microfluidics. Surface tension is much higher when you have gas flows, and inertial forces are important. Hopefully I give you some applications with this will work. And you know, the future outlook for me hinges on two fundamental questions: the compressible flow dynamics effects and controlling this jetting regime, which is way more unstable. I want to finish by acknowledging our funding. Most of it's been from NSF. We have 2 grants, one of them in career. DARPA, the Young Faculty Award, also some of the work that you saw from Stanford was through Honda R&D, and the 2 students, which are always the ones who do the work. Brian Carroll, he was at Texas, he's at JPL now, so close to you guys there. And Puyan Chirandasi, which did all the work here at Northeastern, he's a postdoc at Harvard Medical School now. I had a couple of slides I wanted to show you other work that I'm working on, but since I don't have time, and that way I'm gonna force Beverly to invite me again when I can meet in person.
There we go.
Up there, and thank you for your time, and hopefully for some questions.
Thank you very much, Carlos. A lot of very neat things there. I know some people have had to leave, so hopefully there's some questions from the audience. If you have questions, please pop them in the Q&A or in the chat, and or raise your hand, and we can promote you to be able to ask Carlos directly. If you have to leave, then please go ahead. While people are getting their things together, getting their questions together, their thoughts, I have a really practical question. So you talked about measuring the pressure right at the junction there. How can you speak a little bit about how you do that, please?
Yeah, so we have thought about what are the ways that you could do it, and I'm trying to get to the easier if I do it this way. If I try to go, maybe what's that? So we have thought about creating side channels where you can basically put, you can do probing. Let's see if I can get a picture.
Was earlier on the one.
Yes. This one. So you can try to, for example, if you put, you can create the PDMS little channels here, where you should be able to do something as a pressure transducer, but you could also use a capillary pressure transducer, right? Where you have, you know, a capillary show you what the difference in pressure is between the 2 points. But you have to basically create side channels to probe into the section where you're interested of getting the pressure. We toy a little bit with this sort of micromanometers, where basically you would use the surface tension and the pressure try to quantify the difference by looking at where the interface was in the system. So that's one possible way to do it, but it's not trivial, I would say, because the pressure drops are going to be very, very small. So.
Yeah. Interesting. Thank you. Yeah. Any other questions or comments from the audience? Raise your hand or type it into the chat. I know it's getting to the end of a long week over here, but it's late with you, Carlos. So we certainly appreciate you making time to speak to us here. And the offer absolutely stands. So when things return to normal travel, we owe you an Athenaeum lunch with the faculty. And we hope you'll come visit us another time.
Absolutely, absolutely.
I'm not seeing any